Alright, now we learn about vector products. Now, we have already learned scalar products. So that was, let's say, if A is a vector, n-dimensional vector, made of A1, A2, up to AN. So this is an n-dimensional vector, and B is also an n-dimensional vector, B1, B2, Bn. Then their scalar product. Okay, or it is also called dot product, and we may write like A dot B is defined as A1 times B1 plus A2 times B2 plus and so on. So that is a scalar. In this case, it's a real number. Okay, so the scalar product between two vectors is a real number. Unlike this, vector product, as the name suggests, produces a vector. But it is not defined for any dimensions. It is defined only for three-dimensional space. Okay, we cannot define vector products in the sense that we define here in any other dimensions than 3 dimensions. Okay, so here's the definition. So let's say A is a three-dimensional vector, A1, A2, A3, and B is also a three-dimensional vector, B1, B2, B3. Then the vector product, which we write A cross B. So it's also called a cross product. So this is defined as this. So this is A2 B3 minus A3 B2 and A3 B1 minus A1 B3 and A1 B2 minus A2 B1. So this is the definition. So this is a function. So cross product or vector product is a function from a pair of three-dimensional spaces, vector spaces, to a three-dimensional vector space. Okay, and sometimes we write instead of A cross B, we might write square bracket AB. Okay, and so this is like it's in contrast with scalar product. So this is vector product. This is a scalar product. So this is A cross B is in contrast with A dot B. Okay, so this is a vector product, and this is a scalar product. In this section, we always write a scalar product as dot product, okay, A dot B. And we write cross product as A cross B, or vector product as A cross B. Okay, and you might find this definition a little bit hard to memorize. Now, this is quite complicated at first sight, but there is an easy way to memorize this. So if you define three orthogonal unit vectors, that is E1, 1, 0, 0, E2, 0, 1, 0, and E3, 0, 0, 1. Then A cross B can be formally written as a determinant, matrix determinant. Well, actually, this is not a matrix determinant because here we have E1, E2, E3 as elements of this matrix, but in real matrix, they cannot be vectors. I mean, so we this is just a formal way to express vector product. And A1, A2, A3. So these are the elements of vector A, and B1, B2, and B3. So how do you calculate the determinant? So take the first row, then first pick E1. Oh, sorry. First pick E1, then the remaining vector is this part. Okay, so we have A2, A3, B2, B3 times E1. Okay, then we pick E2, and of course the sign is negative in this case, and we pick this column and this column. So that's A1, A3, B1, B3, and E2. And plus, now pick E3 and consider this part. So that's, and the sign is positive, and that's A1, A2, B1, B2, and E3. So now calculate the determinants of these 2 by 2 matrices. So the first one is, so that's A2 times B3 minus A3 times B2 and E1, and minus A1 times B3, A1 times B3 minus A3 times B1, E2, and the third term is A1 times, A1 times B2 minus A2 times B1 E3. So now let's substitute these elements. Then we have A2, B3, A3, B2, and move this negative sign inside. So inside here we have A3B1 minus A1B3, and the last element is A1B2, A2B1. So this is the cross product, right? Compare this with the original definition. This definition is the same. So cross product or vector product can be defined in terms of, at least formally defined in terms of a determinant. Next, let's see a few properties of the vector product. So here's a theorem. So let A and B be three-dimensional vectors. Then first, if A is zero vector or B is a zero vector, then A cross B is a zero vector. Okay, and 2. If A is parallel to B, so that means if A is a vector like this and B is a vector that is parallel to A, So A, B. So they are parallel. In this case, we can write A is proportional to B, where lambda is a real number, or we can write B is proportional to A, where this mu is a real number. Okay, by the way, this is a Greek letter lambda. Lambda. So there's a B here. And this is a Greek letter mu. Okay. So in these cases, we say A and B are parallel. Okay. And of course, lambda and mu should not be zero. Okay. In this case, let's say lambda is not zero and mu is not zero. Or, okay, in this case, A cross B is a zero vector. Okay. And 3. A cross B is equal to negative of B cross A. Okay. So cross product or vector product is not commutative, but it is actually said to be anti-commutative. Okay, and 4. For any real number lambda, we have lambda times A cross B is equal to lambda A cross B, which is equal to A cross lambda B. Okay, and lastly, 5, E1 times E2 is equal to E3. So these E1, E2, E3 are the vectors we defined before, namely these vectors. Okay, these we say orthogonal unit vectors. Okay, and E2 cross E3 is equal to E1, and E3 times E1 is equal to E2. Okay, be careful of the orders. From the previous this point 3, the order of multiplication matters. Okay, so if we change, for example, E1 cross E2 to E2 cross E1, then the result will be different. That will be negative E3. Okay, so be careful. Now let's prove this theorem. So first one should be easy. So suppose, let's say, suppose A is 0. Okay, in that case, if you look at the definition of, let's say determinant form of the definition. So E1, E2, E3. So if A is 0, we have 0, 0, 0 here, and B1, B2, B3. This determinant is clearly 0, right? So that's 0, 0, 0. For example, if you take this and calculate the determinant of this and this and this, and each of these is 0. So the result is a 0 vector. So that's a 0 vector. And if B is equal to 0, it's the same thing. Just the third row is 0 and the same argument applies. Okay, and second, so suppose let's say B is a scalar multiple of A, where lambda is not 0. Okay, then again let's use this matrix form. So A cross B is this A1, A2, A3, and because of this we have lambda A1, lambda A2, and lambda A3. Okay, and now remember the property of determinant. If you have one row multiplied by a constant, then this is equal to this constant times the determinant without these multiples. Okay, so this should be equal to this. Okay, but now we have the same row here and here, so they have the same values. So in this case, in that case, the determinant is 0. So that's 0. So lambda times 0, so it's 0. In a determinant, if two rows are the same, then the value of the determinant is 0. So you can actually check this. For example, if you take this part, so pick E1 and the remaining submatrix consists of A2, A3, A2, A3. So if you calculate this determinant, it's 0. And same applies for other elements. So that's done. And third, so again, A cross B is this A1, A2, A3, B1, B2, B3. Now recall that that property of determinant. If you swap rows, then the sign changes. Okay, so if you swap the second row and the third row, then the result is negative. Okay, so B1, B2, B3, A1, A2, A3. Okay, then but this is negative of B cross A, right? So this cross product is anti-commutative. And fourth, so lambda A cross B is lambda E1, E2, E3, A1, A2, A3, B1, B2, B3. So again, from the property of determinant, if you multiply a determinant by a constant, then it is same as the determinant of which one of the row is multiplied by that constant. So it should be same as lambda A1, lambda A2, lambda A3, B1, B2, B3, which is the cross product between lambda A1, lambda A times B. Oh, maybe this. Okay. And the same argument applies to the third row, so we should have A cross lambda B also. similarly. Okay, and 5, E1 cross E2. Well, just apply the definition and you should find the result is 0, 0, 1, which is E3. Okay, just in case, let's try this. E1, E2, E3. E1 is 0, 1, 0, 0. E2 is 0, 1, 0. So if you calculate, that's 0 times 0 minus 1 times 0, which is 0. And the second element, 1 times 0 minus 0 times 0 times everything multiplied by negative 1, which is 0. And the third element, 1 times 1 minus 0 minus 0, which is 1. Right? Done. And same for other combinations. Okay, now we define the triple product. Okay, definition of triple product. This is actually easy. Let's say we have three vectors, A, B, and C, which are three-dimensional vectors. Okay, then the triple product is this, A dot B cross C. Okay, this dot means scalar product between A and B cross C. Okay, so in the previous notation, this is this would be written as this, A and B cross C. Okay, and so this is a scalar. So this is a real number. Okay, so this B cross C is a vector in three-dimensional space, and A is a vector in three-dimensional space. So their scalar product is a scalar. Okay, so it's a number, not a vector. Okay, be careful. This is different from this. So order matters. Okay, so if you write, for example, let's say B dot A cross C, this is completely different from this. Okay, they're different. Now, here is a little cute little theorem regarding a triple product. So let's say A, B, C are three-dimensional vectors. Then this triple product, A dot B cross C, can be expressed as a determinant. Okay, here A, B, C, they are row vectors. Okay, so let's prove this. So let's say A has elements A1, A2, A3, and B has elements B1, B2, B3. C has elements C1, C2, C3. And by the definition of cross product, B cross C is this B, so that's B, this B2 C3 minus B3 C2 and B3 C1 minus B1 C3 and B1 C2 minus B2 C1. Okay, so now we take the scalar product, dot product between A and B cross C. So again, from the definition of the scalar product, this is A1 times this, B2 C3 minus B3 C2. and plus a2 and the second element, b3c1 minus b1c3, and plus a3 times that third element, b1c2 and b2c1. Okay. Now, maybe we should swap the sign of the second term. So let's put a negative sign here and change the order of this. So that would be, let's see, so b1 c3 minus b3 c1. Okay, so we just put the minus sign out to here. Okay, then if you look closely, you should notice that this is, no, this is the determinant of this. b2, b3, c2, c3, and minus a2, and b1, b3, c1, c3, and plus a3, b1, b2, c1, c2. But this is the determinant of this 3 by 3 matrix. a1, a2, a3, b1, b2, b3, c1, c2, c3. So that is it. And we are done. Now, because we know that the triple product can be expressed as a determinant of 3 by 3 matrix, then we have the following nice corollary. So that's a corollary. By the way, corollary means a little theorem that can be easily derived from another theorem. Okay, so we say this is a corollary to this theorem. Okay, so we have this result: a dot b cross c is equal to c dot a cross b, which is equal to b dot c cross a. So how is that? A dot b cross c is a determinant, a, b, c. So if we swap the rows of a determinant, then we have, let's swap a and c. Then we have a negative of the determinant, right? So ca. So we swapped a and c, the first row and the third row. Then we have this negative sign. Okay, then if we swap, let's see, the second row and the third row, then we have again negative sign, which will cancel this negative sign. So we have c a b, which is c dot a cross b, and the same holds true for this one. So if we swap from this point, if we swap b and c, then we have b c a, which is b dot c cross a. Okay, so you can memorize this in this way. So this is a, b, c. Then you put a in the third position, then push b to the first position, then you get this expression. Okay, let's write it. So A, B, C. So, and B, C, A. So if we move A to the last position, then B is moved forward and C is moved forward. Okay. Then again, put B to the last position. Then move C to the forward position and A to the forward position. Then you have this. So this is like a circular permutation. Okay. Or is the right word? Circular permutation. So it's like a circle. So A goes back and everything else moves forward, and B goes back, everything moves forward, and so on. Then if you push C to the back again, we are back to the first expression, right? Okay. And here's another corollary. That is A dot A cross B is 0. Okay. Why? Again, this triple product can be expressed as a determinant. So in that determinant, there are two rows with the same numbers. Two rows contain the same vector A. Okay. If two rows are the same in a matrix, then its determinant is 0. So therefore this result. Okay, you should check that. And of course we have B dot A cross B is equal to 0 also. It's for the same reason. Okay. So what does this mean? Okay, let's say in 3 dimensions we have two vectors, suppose. So A and B. Okay, so we if we take the cross product between A and B, then the result is another vector. So it's another vector. Actually, it should be, let's say this is A and this is B because that's easier to write. So if we take A cross B, then the result is some vector. Okay? But that vector, this cross product, is perpendicular to A or B, right? So this is perpendicular, let's write in red. This is perpendicular to A, and this is also perpendicular to B. Okay, so these are right angles. That's what this means. So if you calculate the cross product between two vectors, that cross product is perpendicular to both the vectors. Okay. And actually, if you if you calculate A times B, A cross B, then you have the vector in this direction. Okay, so this is like this. If you rotate A, vector A to B, if that's it's in the anti-clockwise order, so if it's in anti-clockwise, then this vector is up. Well, of course, in 3 dimension, which direction is anti-clockwise or clockwise makes no sense really. But so if you look at this result as this, if you have these 3 vectors, A, B, and A cross B, then if you look down A and B from this direction, so opposite direction of A times B. So if you say, suppose your eyes are here, and looking down A and B, then it looks like you rotated A to B in anti-clockwise direction. Okay, or this is so-called right-handed set. Okay, so if you put a right hand, point, let's see, point this direction using your pointing finger, and point this direction of B using your middle finger, then the direction of A cross B is the direction of your thumb, of your right hand, not left hand. Okay, so it's called right-handed set. Or right-handed coordinate set. Okay. So what if then if you have vectors like A and B, A, B. So in this case, the direction of A cross B is this direction. Okay. So still it's perpendicular to both A and B. You see? So you point this direction using your pointing finger with your middle finger, then the thumb is pointing this direction, right? So that's called a right-handed coordinate system. So this is the convention we usually use in mathematics or physics, right? So that's x, y. So the z direction is this direction, okay? Not this direction. So this is called right-handed set. So if you point this using your pointing finger of your right hand and middle finger, then the thumb should point to the direction of z coordinate, positive z. Okay, it's the same for cross product. Okay, another corollary is this. A cross B plus C. So this is a distributive law. Is A cross B plus A cross C. So you should be able to prove this in either way. You can just calculate this directly using the definition of cross product and vector addition, or you can use the property of determinants, which we have proved in a previous lecture. All right, now we know that A cross B is perpendicular to both A and B, right? And there are more geometric meaning to the cross product, which we will explore now. The first step is to prove this lemma. So if, okay, A and B are of course three-dimensional vectors. If A dot B, so their scalar product is 0, then the modulus of A cross B, the length of A cross B is equal to the product of the moduli of A and that of B. Okay, so the length of A cross B is equal to the product of the lengths of A and B. If A and B are 0, A dot B is 0. Okay, so let's prove this. So proof. if A is 0 vector or B is the 0 vector, then the result is trivial. Because that means A cross B is 0 and A or A modulus or B modulus, they are 0. So that's 0 equal to 0. So it's trivial, right? So suppose A, B are both non-zero. Okay. Since A dot B is 0, we have A1 B1 plus A2 B2 plus A3 B3 equal to 0. This is just the definition of the scalar product. So if we square both sides, so that is, if we square both sides, then we still have the left hand side is equal to 0. So then expand this left hand side. We have a1 square b1 square plus a2 square b2 square plus a3 square and b3 square plus 2 a1 b1 a2 b2 plus 2a2 b2 a3 b3 plus 2 a1 b1 a3 b3 equal to 0. Okay, so if we rearrange this, so move all these parts to one side and move everything else to the other side, then we have negative 2a1 b1. Let's write in this way: a1 a2 b1 b2 minus 2 a2 a3 b2 b3 minus 2 let's see a3 a1 b3 b1 equal to this. So a1 squared b1 squared a2 squared b2 squared and a3 squared b3 squared. It's ugly. b2 squared. Okay, now let's leave this this way. Then we compute this A cross B modulus. Okay, by applying the definition of this cross product, this is just the sum of square of elements of this cross product. So that's a2b3 minus a3b2 squared and a3b1 minus a1b3 squared plus a1b2 minus a2b1 squared. So if you expand all this, okay, then you will have it's a lot of writing, so let's stop. So by expanding all this, so this becomes this, and this becomes this, and this becomes this. Okay, just expand. Now look at this part. So this part is the same as this left hand side. So that means we can replace this part with this summation. Okay, a1 squared b1 squared plus a2 squared b2 squared a3 squared b3 squared. So let's replace this. And we have a2. Okay, let's see. No, okay, forget it. a2 squared b3 squared a3 squared b2 squared plus a3 squared b1 squared a1 squared b3 squared plus a1 squared b2 squared a2 squared b1 squared plus, so this part is replaced with a1 squared b1 squared b2 squared a2 squared a2 squared b2 squared a3 squared b3 squared. Now let's factorize this. How do we do this? Let's see. So we have a1 squared here and a1 squared here, and we have a1 squared somewhere else here. So if we factorize a1 squared out, we have b1 squared b1 squared and b2 squared and b3 squared. Okay, now let's look for a2 squared. Let's see, a2 squared here, a2 squared here, and a2 squared here. And a2 squared here, but there they have also, so that's b1, b2, and b3 squared. So b1 squared, b2 squared, b3 squared. And you will find the remaining terms are a3 squared times the same factor. b2 squared, b1 squared, b2 squared, b3 squared. So that's factorized as a1 squared plus a2 squared plus a3 squared times b1 squared, b2 squared, b3 squared. But this is the modulus of a vector a squared, and this is the modulus of vector b squared. So that was to be proved, and we are done. Before going to the next theorem, let us consider the meaning of this lemma. So this lemma says if just forget about the cases where a and b are zero vectors. So if they are not zero, if their dot product or scalar product is zero, then the length of the cross product, their cross product is the product of the length of these two vectors. Okay. So this means, suppose we have a, b, and a and b. Okay, a and b, and they are they are orthogonal, meaning they have right angle. Okay. Then if we calculate their cross product, so that's a cross b, and as we have seen, the cross product is perpendicular to both a and b. Okay. So here A and B are perpendicular to each other, and by this condition, and A cross B is always perpendicular to A and B. That's the property of the cross product. Then this lemma says the length of this vector. Okay, so this length is equal to the length of A times the length of B. So what does it mean? So just look at A and B on two-dimensional plane. Okay, so let's say this is B and this is A. Okay, so they are perpendicular to each other. So this quantity A modulus times B modulus means the area of this rectangle made by these two vectors A and B. Okay, this area is this, right? So the length of this is A modulus, the length of this is B modulus. Okay, and they have the right angle here because the scalar product is 0. Okay, so the length of the cross product is the same as the area of this rectangle. Okay, so that's what this lemma says. So naturally, we want to extend this result to the case where this angle is not the right angle. Okay, for example, what if we have something like this, A and B? Okay, then we have a cross product. So this is not right angle. Okay, this is right angle. This is right angle, but the angle between A and B, let's say theta, is not the right angle. So in this case, what's the length of A cross B? Is it related to some area made by these two vectors? For example, these two vectors can make this parallelogram, right? So is this length related to this area? So that's the question. And actually this is indeed the case according to the next theorem. So here's the theorem. Again, A and B are three-dimensional vectors, and the angle between them is theta. Okay, just like in this picture. Okay, so the angle is theta. Then we have this relationship. A cross B, its modulus is equal to A modulus times B modulus times the modulus of sine theta. Okay, so this is the theorem we want to prove next. But before that, compare this with the result of dot product. So A dot B, if you remember, this was used for defining the angle between A and B. So that was cosine theta. Okay, since the scalar product is a scalar, it's a real number, so this made sense. But in the case of vector product or cross product, the result of the product is a vector. So by itself, it's we cannot say not much about the size of it. So if we just calculate the modulus of that vector, then we have this relationship. Instead of cosine, we have sine here. But since the modulus is always non-negative, so we have this absolute value of sine theta. Okay, this theta is the same as this theta. Okay. Now, what is this sine theta? Okay, think this way. Suppose we have two vectors A and B. So this is A and this is B. Okay, and their angle is theta. So there are 3 points. This point, and this point, and this point. So these 3 points define a triangle. Okay, and a triangle resides in a plane. In other words, this triangle defines a plane. Okay, so we redefine our x and y axis as this. So let's define x as this axis and y-axis as the axis that is perpendicular to x-axis and also within this same plane of as this triangle. Okay, so this triangle defines a plane. So within this plane we define this x-axis and y-axis. Okay, then let's say this length is b modulo times sine theta, right? Because within this axis we can define a coordinate system, two-dimensional coordinate system. So that would be b modulo cosine theta and b modulo sine theta, right? So this y coordinate is this. So this height, well, I said height, but it is height actually. So this length is b modulo sine theta. Of course, it should be a absolute value because this theta can be negative, right? But anyway, so since this height is this, then if we want to calculate the area of this parallelogram, okay, this one, and the length of this base here, that is a modulo. So this area is this length of base and this height, that is b modulo times modulo sine theta. So this is the area of this this shape. Okay, so this theorem says the length of A cross beta is the same as this area. So let's move on to the proof, and the proof is actually based on the intuition we have just provided. So first of all, we have a dot b equal to a modulo times b modulo modulus and times cosine theta. Okay, because the angle between a and b is theta, so this was the definition of the angle between two vectors. So we have this equality. Now next we define a unit vector a hat by this. So we multiply vector a by the inverse of a modulus. Okay, this is a unit vector. That means a hat um, has length of 1, and so you should be able to see this from this definition. Next, we define B parallel. Okay, this means okay, let's just define it first. A hat dot B, so this is a real number. This is a real number times a hat. Okay, why is this called B parallel? Okay, so let's see. So this is B, and let's say this is A. Now, a hat is a unit vector. So let's say suppose this is a hat. Okay, so a hat is in the same direction as A, but it has a unit length. So a hat dot B had some length. That length is actually same as this. If you project this vector B onto the direction of vector A, then you have this length. So it's the length of the projection of B on A. Okay, so this vector is B parallel. Okay, so it is the component of B that is parallel to A. Okay. So as you have seen before, this dot product is actually the product of modulus times cosine, right? But a hat is a unit vector, so this is B modulus times cosine theta. So this length of this projection is equal to this. Then, using this, we define B perpendicular. Okay, and that is defined by B minus B parallel. Okay, so what is this vector? So if you subtract B parallel from B, then that vector becomes this. So B, first add B, then subtract B parallel. So the direction of B parallel is reversed. So let's see, going here. So starting from here, we go here, minus B parallel and plus B. So that is the resulting vector is this, from here to here. So that is perpendicular to A. So this is the component of B that is perpendicular to B. Perpendicular to A, sorry. So in other words, we have, so this means B, vector B is the sum of B parallel plus B perpendicular. Okay, so this vector B is decomposed into two components which are perpendicular to each other. Okay, and we can actually show that B perpendicular is indeed perpendicular to A. So let's just take the dot product between B perpendicular and A hat. Okay, and by definition, B perpendicular is B minus B parallel, and times A hat. Okay, then that is B a hat minus, and B perpendicular is this. So just substitute. Sorry. So a hat dot B times a, this is not dot, times a hat dot a hat. Okay, so this is a dot product. And then, but this is this part. This part is equal to the modulus of a hat squared, which is 1. So this disappears. So we have a hat dot B and B dot a hat. Of course, dot product, scalar product is commutative, so this is 0. So this is equal to this. This is equal to this. So it's 0. Therefore, this vector B perpendicular and a hat are perpendicular to each other. Okay. And of course, parallel is parallel to a hat. So we have, we also have B perpendicular dot B parallel is 0. So they are perpendicular to each other. Okay, so just calculate the modulus of B perpendicular squared using the definition of this vector. Let's see, B perpendicular, wait a minute, what is it? Is, let's see, B minus B parallel that is sorry, no, not this one. So anyway, we have B equal to B perpendicular plus B parallel. And so if we take the modulus of both sides, we have this. However, since the dot product between this and this is 0, so we have B perpendicular squared plus B parallel squared. Okay, so from this, we can move this to the other side. Then we have B perpendicular square equal to B squared minus B parallel squared. But as we have seen, B parallel square, this one, is equal to B modulus times cosine, okay, squared. So B modulus minus B modulus squared cosine squared 0. So we factorize, that is 1 minus cosine squared. But 1 minus cosine squared is sine squared. Right? We have this equation. Cosine squared plus sine squared is equal to 1 for any theta. So, therefore, we have the length of B perpendicular is equal to the length of B times absolute value of sine theta. Okay, now consider the vector product A cross B. But B is, of course, B perpendicular plus B parallel, and A cross B perpendicular plus A cross B perpendicular. However, B parallel is A B perpendicular B parallel, but A and B parallel are parallel to each other, right? So this cross product becomes 0. So this is 0. So we are left with this. And remember, A dot B perpendicular is 0 because the way we made B perpendicular, right? So that means the modulus of this is equal to the modulus of A times the modulus of B perpendicular. But the modulus of B perpendicular is this. So that is A modulus B modulus times sine theta modulus. So that's the result we wanted to prove, and we are done. So now you understand that the cross product between two vectors represents somehow the area made by the area of the parallelogram, or made by the two vectors. So if we have A and B, then the area here corresponds to the length of their cross product. Okay. Now, if we have three vectors, A, B, C, and we can consider the triple product A dot B cross C. Then actually this corresponds to the volume of the parallelepiped. This is an unfamiliar word for me. Parallelepiped made by these three vectors. Okay, so what this means is this. So we have, let's say, maybe it's easier if we consider B, C, and A. So we have this parallelogram, and we have this parallelogram. So this means this is a very lousy picture of a parallelepiped made by these three vectors. What I mean is, let's see, this face is parallel to this face, the opposite face, and this face at the bottom is parallel to this face at the top, and this face on the right is parallel to that face on the opposite side. So, and every face is a parallelogram. So this is a parallelogram, and this doesn't look like a parallelogram, but it should be a parallelogram. Okay. Okay. So this dot product corresponds to the volume of this solid. Okay, how is it so? So now, let's see. So B cross C is the area, is this area, right? And and also this cross product points to this direction. That is perpendicular to both B and C, right? So if we take, okay, so this is B cross C. If we take the dot product between A and B cross C, then what is that? Okay, so there should be some angle. Let's call it let's call it phi. Okay, so there's an angle between A and B cross C. Let's call it phi here. So if you project this vector A onto B cross C, then that length, this length, is equal to this A modulo times cosine phi. Okay, so let's look at this parallelepiped from this side. Okay, where B and C are in the same plane. Okay, B and C on the same plane. So this is A, and this is B cross C. So that is perpendicular. And so the parallelepiped looks like this, something like this. So this is a parallelogram. This is B, and C is somewhere on this plane. So the height of this parallelepiped is this. But this length is cosine theta times A modulus. Okay, so that means A dot B cross C represents this A modulus and B cross C modulus times cosine theta. But this B cross C represents the area of this face, right? So this face, this face. So this area times this height means the volume of this parallelepiped. Okay. So this triple product corresponds to the volume of this solid. However, it has a sign. Okay. It may be positive or negative. In case A and B cross C are pointing to more or less the same direction, that is, the angle between them is less than 90 degrees or half pi, then this is positive. Otherwise, it can be negative. Okay, if A is perpendicular to B cross C, that means A should reside in the same plane as B and C. So in that case, the volume is 0. And if A is pointing the other direction than B cross C, then the volume is negative. So it is a signed volume. So if you take the absolute value, then it is just a volume, but it is signed. So it implies the direction of A with respect to B and C. Okay, so if the volume is positive, then the coordinate system A, B, C, they make the right-hand system. And if the volume is negative, then it is a left-handed side, left-hand set. Okay, so that's the meaning of cross products. So now you know triple product is related to the volume of a solid that is determined by three vectors. But also you know that the triple product is the same as the determinant of a matrix made from these three vectors. So A dot B cross C is the determinant of a matrix, right? Actually, if you consider two dimension, so let's say in this case, suppose A is a two-dimensional matrix, A, B, A1, A2, and B is another two-dimensional vector, and consider this matrix determinant A1, A2, B1, B2. That is A1, B2 minus A2, B1. So in this case, if you consider these in the two-dimensional space, so suppose this is A1, A2, and suppose this is B1, B2. But this determinant corresponds to the area made by these two vectors, the area of this parallelogram made by these two vectors. So this area corresponds to this determinant. And also this is signed area. So when A is here and B is here, then this is positive. But in case where A is here and B is here, this is A and B. So in this case, this area is negative. You should try to prove this by using some geometric argument. And similarly, for any dimensions, suppose n-dimensional matrices, let's say A1 is a vector in n, let's say A1, A2, so they are vectors, AN, they are vectors in n-dimensional space, vector space. Then the determinant defined by these vectors corresponds to the volume of the solid defined by these n vectors. Okay, in two dimensions you need two vectors to define some two-dimensional shape. So that is a parallelogram. In three dimensions you need three vectors. So one, two, three vectors to define a parallelepiped. Although it may be difficult to imagine, in four-dimensional space, you need four vectors to define some solid corresponding to something like the parallelogram in two dimension or parallelepiped in three-dimension space. There is some analogous object in four-dimensional space or in any dimensional space. And of course, we can define the volume of that solid, and that is calculated by this determinant. Next, we move on to the topic of linear independence and dependence. This is a very important concept which you should be very familiar with to work in any field in mathematics or in physics or in chemistry. Okay, so there are many kinds of independence in mathematics, and this is a very basic one. Okay, so first we define linear dependence. Okay, linear dependence. Okay, so let's say we have a set of vectors v1, v2, up to vm. Okay, in some vector space. Okay, we don't specify the dimension here, so it can be anything. Okay, so this m and this n may be different. Okay, so they are said to be linearly dependent. So in a sense, they depend on each other linearly. Dependent if there are real numbers, lambda 1, lambda 2, up to lambda m, such that lambda 1 v1 plus lambda 2 v2 plus and so on, lambda m vm is equal to 0, and not all lambda I are 0. Okay, so this means some of these lambdas may be 0, but not all of them. So some must be non-zero. Okay. So if this is the case, so if there are some lambdas that are not 0, but the linear combination of these vectors happens to be 0, then these vectors are said to be linearly dependent. Okay, so what does it mean? So, for example, suppose lambda 1 is not 0. Okay, so this means lambda 1 v1 is equal to negative lambda 2 v2 plus lambda 3 v3 and so on, lambda m vn m. So since lambda 1 is not 0, we can divide both sides by lambda 1. So lambda v1 can be expressed as this, lambda 1. So in other words, so v1 can be expressed as a linear combination of all other vectors. See? So v1 is actually a linear combination of other vectors. So in this sense, v1 depends on other vectors, so they are linearly dependent. Okay, so here comes the definition of linear independence. Linear independence. As you might guess, linear independence means not linear dependent. Okay, so v1, v2, and vm are said to be linearly independent. if they are not linearly dependent. So what does it mean exactly? So since the definition of linear dependence is such is this, there exists some non-zero lambda such that the linear combination is zero. So if these vectors are not linearly dependent, that means the negation of this proposition, this statement is true. So that means this. Uh, if uh, lambda 1 v1, lambda 2 v2, and lambda m vm is 0, then it means lambda 1, lambda 2, they are all 0, equal to 0. And only in this case, this linear combination is 0. Okay. So this means v1, v2, and up to vm, they are linearly independent. Okay. And of course, if they are all 0, this is trivially 0. So we can say this is if and only if. Okay. But the important part is only if part. Only if they are all equal to 0, this is a linear combination of all these vectors is 0. There are no other cases. Okay, so that's what linear independence mean. Okay, so since linear independence is the opposite of linear dependence, this means no one of them, no one of these vectors can be expressed in terms of other vectors, right? So we cannot write v1 equal to some linear combination of v2 to uh, vm. It's not possible. Okay, and same for v2. v2 cannot be written as a linear combination of any other vectors. So in this sense, they are all independent of each other. Okay, then let us introduce an important theorem. Okay, so let v1, v2 up to vm are linearly independent. Independent vectors. So suppose and then if there is a vector u such that it can be expressed as a linear combination of these vectors, beta 1 v1, beta 2 v2 up to beta m vm. So if u is a linear combination of these vectors, then uh, this representation is unique. This representation of u this means this linear combination of u is unique. So, so maybe this is not clear. So, what does it mean? This is unique. So this means if there is another linear combination, let's say, so these are beta. So by the way, this is a Greek letter beta, okay, beta or beta. Let's say there is another linear combination of these vectors, such that so that this vector, the same vector u can be represented by this linear combination. Okay, so this is gamma, uh, Greek letter gamma. Gamma 1, V1, gamma 2, V2, and gamma M, Vm. Okay, then so this beta 1, V1, and this V1, they are, of course, the identical vectors. So if there is another linear combination of these vectors, so but this u and this u, they are the same u, then beta 1 is equal to gamma 1 and beta 2 is equal to gamma 2, and so on. So all those coefficients of vectors are the same. So beta m is equal to gamma m. So this means, so this is what this uniqueness means. Okay, so this is actually what we want to prove. So let's prove this. So suppose there is another representation. Another representation, another linear combination. Another representation. So that is this. Okay, then we have beta 1, V1, beta 2, V2, etc. Vm is equal to gamma 1, V1, gamma 2, V2, etc. Gamma m, Vm. So moving everything on the right hand side to the left hand side and factorize by the vectors, we have beta 1 minus gamma 1 times V1 and beta 2 minus gamma 2 V2 and so on, and beta m minus gamma m Vm. Okay, but beta 1 up to beta m are linearly independent. So this is a given condition, right? So okay. So this is a given condition. These vectors are linearly independent. But by the definition of the linear independence, therefore, all these coefficients must be equal to 0, right? Otherwise, they are not linearly independent. Therefore, beta 1 minus gamma 1 is equal to 0, beta 2 minus gamma 2 is equal to 0, and so on. Beta m minus gamma m equal to 0. Therefore, so this means beta 1 is equal to gamma 1, and so on. Therefore, the representation is unique. Unique. And we are done. The notion of linear independence and dependence had something to do with determinants of matrices. And the following theorem is actually a corollary to a previous theorem. So suppose we have a matrix which is represented as a vector, column vector of row vectors. Okay, so A1, A2, and AN. So this is a n by n matrix. Okay, so of course this A1, A2, and AN, they are n-dimensional row vectors. Okay, then if A1, A2 up to AN are linearly dependent. Okay, dependent. Then the determinant of this matrix is 0. So then determinant of A is 0. Okay. So let's prove this. So without losing generality, we may assume that, okay, proof, without, so this is a idiom, but don't abuse it. Without loss of generality. You should know what you're talking about when you use this phrase. We may assume AN. So this last row is a linear combination of all other vectors. A1, A2 up to AN minus 1. So why can we assume this? You know, maybe A2 is a linear combination of all other vectors, not AN. No, not all of them may be expressed as a linear combination of other vectors. Only some of them can be expressed as a linear combination of other vectors, so that this set of n vectors is linearly dependent. Okay. So why can we assume this last row in particular can be expressed as a linear combination of all other vectors? Maybe we cannot, but if we cannot, we can always swap the rows so that the last row is always a linear combination of other rows. Just swapping the rows doesn't change the value of the determinant except for the sign. Okay, but in this case, the sign doesn't matter much. No, it's not so important. What's important is whether it is 0. The determinant is 0 or not. Okay, that's all we care here. So if we cannot actually express the last row as a linear combination of other rows, then we just swap some other row to the last row. Okay, so that's what we mean by without loss of generality, or without losing generality. We may assume this. Okay? So that is, so say we can write AN as a linear combination of all other vectors, lambda 1 up to lambda n minus 1, a minus 1. Okay? Then this determinant an minus 1 an is this. So a1 up to an minus 1, lambda 1 a1, and up to lambda n minus 1 a n minus 1. Okay, but the determinant is linear in every column, so we can split this determinant into the sum. So a1 lambda 1 a1, so an minus 1, plus a1 up to lambda a n minus 1, lambda 2 a2, and so on. So up to this a1 a n minus 1 a lambda n minus 1 a n minus 1. Okay, and also we can put each constant scalar out of the determinant. So this becomes this a1 a n minus 1 a n a wait a minute, a1, and lambda 2 a1 a n minus 1 a2, and lambda n minus 1 a1 a n minus 1 a n minus 1. But look at every term here. We have the same rows a1 and a1, and here there is a2 here, and there is a2 in the last row. So every determinant in this, every term contains two same rows. But in those cases, we know that the determinant is 0. Now, if two rows are the same, then the determinant is 0. Therefore, this is equal to 0. So every term is 0. So this is 0, 0, 0. So everything is 0. Therefore, the determinant is 0. Okay. Now, the contrapositive of this theorem is the following. Okay, so it's a corollary. So let's say we have a matrix A that is made of all these column vectors. Then the contrapositive of the last theorem is this. If determinant of A is not equal to 0, then all the rows, so a1 a2 up to an, are linearly independent. Okay, so this is just a contrapositive, so it should be true. It's trivial. But the real interesting thing is that the converse of this is this. If these vectors are linearly independent, then the determinant is not 0. So that's the converse. And the converse is also true. But we cannot prove this here. It requires more preparation. So after all, we have this determinant of A is not equal to 0 if and only if those column vectors, those row vectors, well, it's also the case for column vectors too, and these row vectors are linearly independent. So this property is exploited when we want to solve the system of linear equations, for example. And that's all for uh, the linear algebra for this module. But the field of linear algebra is very huge. So there are many things we cannot explain in this module, and I hope you will learn more in some other modules. And I would say linear algebra is the single most important subject in university mathematics. So please study hard.